So, today our first speaker is Alcides Lins-Neto from IMPA, with the title is on the number of solutions of these special polynomial equations, which is part of the 16th Hilbert problem. Please.
Thank you. So I would like to thanks Jose for inviting me. Okay. So this work I did more or less 40 years ago, and but Jose told me to talk about because it's related with the conference. So. Huh? So.
Hussein announced the conference as a conference on the Hilbert 16th problems, but at the end is a conference about the center follows problem.
Okay. Well, this is a kind of particular case of Hilbert's 16 problem. Okay? For instance, if you some types of differential equations you can reduce to this case, to this problem. So, for instance, this foliation of degree 2 in R2 some facts about this vector field is that any straight line of the plane, if it's not invariant then it is tangent to the vector field in 2 points counted with multiplicity. So you can prove, using this, you can prove that if the equation has a closed orbit, then it is convex. The region of R2 bounded by the closed orbit contains just one singularity, and the eigenvalues of the derivative are complex, not real, okay? That's it's not alpha plus or minus beta plus alpha plus or minus I beta. I forgot an I. Okay? So, well, after an affine change of variables, the equation, this is a affine change of values, you take polar coordinates, then the equation can be written in this way. And the denominator is exactly the equation of the, well, the lines I'm considering to express in polar coordinates are the lines passing through the singularity. And then these lines are tangent to the vector field at the singularity and at one more point. And so 1 plus h of theta r equals 0 is the equation, the polar equation of the other point, okay? When theta varies, then, okay. So you can reduce to this form, the equation. And after you do another change of variables, rho equals R over 1 plus HR, then in this way, the curve of tangents 1 plus HR goes to infinity, and you find this equation, which is of the form I have considered before, no? But degree 3. And F1 and G1, polynomials in cosine theta and sine theta. So after some manipulation, just a minute. If you no, it's not this. Oh no, it's page 9. It's missing something. Oh, it's missing something. So I have to continue in the blackboard. So my problem is the knee. My knee is... So the first theorem is, suppose you have an equation of degree 3. And suppose that A3 of t bigger equal to 0. So I'm considering, no? And so these functions, the coefficients, are, I would suppose, the polynomials or functions, periodic functions, anything you want. No? But suppose you have this condition, then the equation I will call star has at most 3 solutions such that okay. So I'll give an idea of the proof. So the proof is, suppose you have 3 solutions. I'll prove that you cannot have more than 3, okay? Well, this condition is A3 of bigger equals to 0, but A3 is not identically to 0, no? If A3 is identical to 0, then you have a equation of degree 2, and so it's you have at most 2 solutions. So the proof goes like this. So suppose x1.
So you mean if you have more than 3, then you have infinitely many?
Huh? I prove that there is no more than 3, okay? So suppose you have 3, okay? And I will prove that no other solution is closed. I call closed if satisfies this condition, okay? So it's like an equation in the cylinder, no? 0, 1, cylinder, 0, 1, okay? So the proof goes like this. First of all, I do a change of variables like that, okay? So if I do this change of variables, then so I will find something like so y equals 0 now is a solution, okay? So since y equals 0 is a solution, okay? The other solutions are not equal to 0, okay? So identity, no? The solution x1, x2 goes to this solution y2, no? So now I do another change of variables. Zeta equals y. Since y2 is not equal to 0, I have the right to do this change of variables. And I find so the thing is that now in the z-plane, no, I will have two constant solutions. Y equals 0 goes to z equals 0, and another solution is z2 equals 1, identically 1. So then the new equation of is let me go.
Y equal to Z.
Huh?
Y equal to
Z.
Z.
Z. And the thing is that C1 is also bigger equal to 0, okay? You can find explicitly C1, and then so I write in this form. Okay? No, now I will since this form is closed, no? I integrate both sides So I suppose we have another solution, Z3 of t, okay? And this, and I integrate it in some solution, okay? Z of t, okay? Z of t. Then this integral gives logarithm oh, this form, dz, z. Okay? So I find another solution with initial condition different from 0 and 1, okay? Then I find, I'll call z of 0, z0, z1, z1. Then I find something like this, okay, is equal to the integral of, from 0 to 1 of C1 of t, z plus C0 of t, here, t, no? dt, okay? Now suppose you have two solutions, two more solutions, Z3 of t, and take another solution, okay? Then, well, if the orbit is closer, then this gives 1, log of 1, 0, okay? Then this integral must be 0, okay? So suppose you have two solutions, two closed solutions by absurd. Then you subtract this. So you have Z3 and another solution, Z, and subtract this. So I must have Z of t different from Z3, no? For all t. Now suppose that Z of t is bigger than Z3 of t for all t. So I subtract the equation with Z3 and with Z. Then I have C1 of t, Z of t, minus Z3 of t, dt, must be 0, okay? But this is bigger than equal to 0, and this is bigger than 0, okay? And this is not identically 0. So this integral cannot be 0, okay? So you have at most 3 closed solutions, okay? Well, now, theorem 2 is that if you don't assume this condition, A3 bigger than equal to 0, something like this. So if you allow A3 to be 0 someplace, then you can have any number of solutions. So the theorem is that for any k exists an equation, huh? There exists an equation like star with k closed solutions. Okay? The proof is technical, but
So are you claiming that these solutions are isolated?
it's isolated, yes. Not center. No, it's not a center, okay? Isolated. Well, the trick here is to in fact, I consider the equation like this. Abel's equation, okay? So the trick, this equation has x equals 0 as a solution. And you can consider the, the map, Poincaré map from this. Well, there are some solutions going to infinity, okay? Maybe. But the solutions near x equals 0, beginning near equals 0, must cut the other t equal 1. So you have the map, the holonomy map, F. That the fixed points of this map are the closest solutions, okay? So the trick is to work to find the coefficients in such a way, so you perturb, you consider okay? And consider this, the equation in this form. Epsilon is a parameter, okay? And I will assume that this is 0. So if this is 0, when epsilon equals 0, is the center, okay? F epsilon okay? The center is easy to see because the equation can be integrated, no? Integrated like this, okay? So you see that the integrate, okay? Here, you see that all the solutions are closed. All the solutions which cut the, no? Maybe there are some solutions, some solutions that go to infinity like this, okay? That's the trick. I think that the part of the where is this is the end of the proof. The end of the proof. So this W of Tx is what is this? This is I don't remember now, but okay. But the idea is exactly to make the perturbation like that, and the problem is that I lost the I didn't check the I had in my phone, but I've lost my phone else. Well, that then. But the idea is this W is what is this W? This W is the you have the, let me call x of xt, phi of xt is the flow, no? Phi tx is the flow, is the solution such that I'll call okay, the solution when you consider epsilon as a parameter, okay, x is the initial condition, so phi 0 x epsilon equal x, okay. And this W, what is this W? This W is the phi, the x, okay? Okay? So, this W satisfies this equation. Huh? Linear equation, okay? When you assume phi, that you know the solution phi here, this W is a kind of variation. Well, this f of t is and in fact, this W is when you take a derivative with respect to epsilon, no? Derivative with respect to epsilon. Epsilon equals 0 is the W in the blackboard. Okay? And And phi 0 is the solution, no? It's the solution with epsilon equal to 0. So I don't remember exactly, but is a if you write me, I send the paper for you, okay? But the idea is to perturb the equation like this and huh?
A3 and A2, the only condition is this some integral.
So the point is that this is to find this W is it gives the asymptotic W equals 0 gives the asymptotic closed solutions. Okay, when epsilon goes to 0, the solutions converge to the roots of W equals 0. Okay, so if you can guarantee that the alphas in the series, the alpha 0, alpha 1, etc., until alpha k equals 0, okay? And then you have at least, so the W is x k, k, x power k. You find just until alpha k minus 3 equals 0, then you have to find the function f such that the alpha g is 0 until some level. Okay, that's the trick. Okay, and so the idea, no? So let me recall. Let me recall the. I have the phi, the flow, no? Phi of t x epsilon. Okay, and then I take the derivative with respect to epsilon. Okay, and no, I don't remember if with respect to yes, with respect to epsilon. So this is it's called Melnikov. No?
This is what we call now it Melnikov function.
What?
Melnikov function.
Melnikov function. Yeah, yes. So I'll finish now because I don't have the.
Questions?
Do you remember, you say that there exists a differential equation like this, and then there is A3 and A2.
What?
So in your second theorem, you claim that for each k there is a differential equation like that with A3 and A2. So you do you remember how you construct this A3 and A2? Because I saw just only one integral condition.
You need the alpha j to be 0 up to k minus 3, so you're going to have a 0 for the.
Okay.
Well, the point is that I don't remember exactly
Okay.
what was written in the but if you want, I'll send you when I took the copy, must
But
some
do you write
problem.
down also a rational function in A3, A2 explicitly? No.
What?
Do you write rational functions A3, A2 explicitly?
Yeah, the AG is a power G of A. A is depends only of F, A3 and F, okay? Okay, the A.
No, that's not the question.
What's the question?
The question is, what's the nature of the functions that you
A,
construct in theorem 2?
Ah,
The nature of small a and A3.
it depends of the coefficients. If the coefficients are polynomials, it's a polynomial, okay? It's a polynomial in cosine t, sine t, is also polynomial cosine t, okay? So the function A is defined by only by the A3, okay? And so you have to find the F there such a way that the alpha j's are 0 until some step, okay?
And he's asking if your
It's possible to do that. In the paper, I have proven. Huh?
I think Hussein asked if you construct your F explicitly or is it just an existential result.
Existential, okay? Well, you have, this is the A power G is because you have the fraction, no? The fraction. So this is the coefficient of xg, x power g in the series, okay? So the coefficient, f is a polynomial, so the coefficient, you have to solve a linear system, okay? A linear system. So suppose you want to set alpha 0 equals 0, no? For instance, okay? So you have to find the f in such a way that the integral from 0 to 1 is 0, okay? Okay? Suppose you want alpha 1 equals 0. Then you have now, you have alpha 0 and alpha 1. Then you have two coefficients of f. The two coefficients give a system, linear system, okay? A linear system, homogeneous linear system, okay? You want to prove that this homogeneous linear system has a solution, okay?
This is, in fact, your, if I remember well, your paper in Invenciones.
Invenciones, yeah.
That so you don't need a preprint.
Invenciones,
40
but I
years
don't
ago.
have the exact
so now
reference.
From more, how to say, contemporary point of view, it is something that Hossein explained in his talks, maybe, that you have a perturbation, and without the perturbation, we have integrable systems in the sense that the holonomy map is identity. And so you perturb and you apply the methods since Poincaré, which is just this. And the functions which detects the limit cycles is this W. The zeros of these functions, they correspond,
Okay.
right? So you find that you have no more than K, you can create K0, so K limit cycles of this function.
Yes, yes.
Just explicitly. And in this context, I remember also, but we didn't speak about this, if I'm not mistaken, there was a sketch of another proof of the theorem which says that when you take polynomials like here, with small degrees, you cannot have more than maybe 3 limits, something like this, but the proof was quite different. You proved that the holonomy is a rational function. I'm right or not? It is a completely
Rational
different
function?
idea
No.
of proof. It was just sketch of a proof, another proof of the same theorem in the polynomial case. When you show that the holonomy is automorphism of, and so it's rational. Something like, no?
It's not rational.
Okay.
I don't think it's rational.
Okay. No, maybe not rational, polynomial, not.
Huh?
Polynomial, rational. No, okay. Maybe I'm mistaken, but it seems to me that you discussed a different proof, but just a sketch of this proof. Going into a complex domain this time. No? Okay. So, other questions?
So in this article, you never complexified, or
What?
you complexified this differential equation to do something, or just the real context?
The real case.
No. But after this article, you started to do complexification of...
No, I didn't consider.
No,
The complexification of this problem.
yeah.
Interesting problem, but I didn't consider it. But the time is real. X is complex, and the time is real. That's your setting.
I mean, you consider the holomorphic foliation in
In C2. In C2. T and X are complex, you mean? I don't know.
Other questions? So let us thank to the speaker.